Alright, so let's dive into the fascinating world of flight and discuss the four fundamental forces that make it possible for airplanes to soar through the skies. These forces are lift, drag, thrust, and weight. They all work together in a delicate balance to keep an airplane airborne and moving forward. First up is lift. Lift is the force that opposes the weight of an object, in this case an airplane, and allows it to rise into the air. It's created by the pressure difference between the upper and lower surfaces of an airplane's wings. As the wings move through the air, they create a pressure difference that generates lift, allowing the airplane to climb. Next, we have drag. Drag is the force that opposes an airplane's motion through the air. It's created by the friction and turbulence that occurs as the airplane pushes through the air. The shape of an airplane, especially its wings and fuselage, plays a significant role in minimizing drag, allowing it to move more efficiently and with less resistance. Now let's talk about thrust. Thrust is the force that propels an airplane forward through the air. It's generated by the airplane's engines, which can be powered by various means, such as piston, jet, or turboprop engines. The thrust provided by these engines needs to be strong enough to overcome the drag force and propel the airplane at a sufficient speed to maintain flight. Finally, we have weight. Weight is the force that acts downward due to gravity and tries to pull the airplane back to the ground. The weight of an airplane includes its own mass and the mass of everything inside it, such as passengers, fuel, and cargo. To maintain a stable flight, the lift force must be equal to the weight force, so the airplane neither climbs nor descends. So in summary, the four fundamental forces of flight, lift, drag, thrust, and weight, all work together in a delicate balance. Lift opposes weight, allowing the airplane to rise into the air, while thrust overcomes drag to propel the airplane forward. By understanding and manipulating these forces, we can design and control airplanes that can take to the skies and transport us around the world. Now that we've discussed the four fundamental forces of flight, let's delve deeper into the Bernoulli's principle and how it helps us understand the generation of lift by an airplane wing. The Bernoulli's principle is a fundamental concept in fluid dynamics and plays a crucial role in explaining how air flows over the curved surface of an airplane wing. The Bernoulli's principle states that as the speed of the fluid, like air, increases, its pressure decreases, and vice versa. In the context of an airplane wing, this principle explains how the air flowing over the wing's curved upper surface moves faster than the air flowing beneath the wing. As a result, there's a pressure difference between the upper and lower surfaces of the wing. This pressure difference is what generates lift. The lower pressure above the wing and higher pressure below the wing create an upward force that opposes the airplane's weight, allowing it to rise into the air. It's important to note that the shape of the wing, specifically its airfoil design, plays a significant role in creating this pressure difference. So, the Bernoulli's principle provides us with a fundamental understanding of how lift is generated by an airplane wing. By designing wings with the right curvature and airfoil shape, we can optimize the pressure difference between the upper and lower surfaces, maximizing lift and enabling airplanes to take to the skies. Let's move on to the fascinating concepts of airfoil design, angle of attack, and wing shape, which play a critical role in determining the lift and drag characteristics of an airplane. These elements are essential in designing an airplane that can efficiently take to the skies and maintain stable flight. First, let's discuss airfoil design. An airfoil is the cross-sectional shape of a wing, and its design has a significant impact on the lift and drag generated during flight. A typical airfoil shape features a curved upper surface and a flatter lower surface. This design helps create the pressure difference we discussed earlier, which generates lift according to Bernoulli's principle. There are various types of airfoil designs, each with its unique characteristics suited for specific flight conditions and aircraft types. Next up is the angle of attack. The angle of attack is the angle between the wing's chord line, an imaginary straight line from the leading edge to the trailing edge, and the relative airflow direction. Adjusting the angle of attack affects the lift and drag generated by the wing. As the angle of attack increases, lift increases up to a certain point, known as the critical angle of attack. Beyond this point, the wing will stall, meaning it loses lift rapidly, which can be dangerous during flight. Pilots must carefully manage the angle of attack to maintain optimal lift and avoid stalling. Finally, let's talk about wing shape. The overall shape of an airplane's wing affects its performance, including lift, drag, and stability. Several factors influence wing shape, such as aspect ratio, the ratio of wing length to its width, wing sweep, the angle at which the wings are swept back, and wing dip devices. Each of these factors can be tailored to optimize an airplane's performance for specific flight conditions. In summary, airfoil design, angle of attack, and wing shape are essential concepts in determining an airplane's lift and drag characteristics. By understanding and optimizing these factors, engineers can create aircraft that perform efficiently and safely in a variety of flight conditions. Now let's take a closer look at the various types of aircraft engines, such as piston, jet, and turboprop, and how they generate the crucial force of thrust to propel airplanes through the air. First, let's discuss piston engines. Piston engines are commonly found in smaller aircraft, such as general aviation planes and light sport aircraft. These engines work by converting the linear motion of pistons into rotational motion, which drives a propeller. The propeller then pushes the air backward, creating a forward thrust that propels the airplane forward. Piston engines are known for their reliability and efficiency at lower altitudes and speeds. Next, we have jet engines. Jet engines are commonly used in commercial airliners and military aircraft due to their high speed and efficiency at higher altitudes. A jet engine works by compressing incoming air, mixing it with fuel, and igniting the mixture, which creates a high-pressure exhaust gas. This high-pressure gas is then expelled through a nozzle at the rear of the engine, generating thrust. There are different types of jet engines, such as turbojets, turbofans, and ramjets, each with its unique characteristics and applications. Lastly, let's talk about turboprop engines. Turboprop engines combine elements of both piston and jet engines. These engines use a gas turbine, similar to a jet engine, to drive a propeller, like a piston engine. Turboprop engines are known for their efficiency and performance at lower altitudes and speeds, making them suitable for regional airliners and various military aircraft. In summary, piston, jet, and turboprop engines are the primary types of aircraft engines, each with its unique characteristics and applications. They all generate thrust to propel airplanes through the air, overcoming drag and allowing the aircraft to maintain stable flight. Understanding the different types of engines and how they work is essential in the fascinating world of aviation. Finally, let's investigate the role of aircraft control surfaces, such as ailerons, elevators, and rudders, which are crucial components that allow pilots to manipulate the forces of lift, drag, and thrust to steer and stabilize the airplane during flight. First, we have ailerons. Ailerons are movable control surfaces located on the trailing edge of each wing. They work in pairs, with one aileron moving up, while the other moves down. When a pilot moves the control stick left or right, the ailerons deflect accordingly, causing the airplane to roll or bank. This movement allows the pilot to initiate turns and maintain balance during flight. Next up are elevators. Elevators are located on the horizontal stabilizer at the tail of the airplane. They control the pitch, up or down movement of the aircraft. When a pilot pulls back on the control stick, the elevators deflect upwards, increasing the angle of attack and generating more lift. This causes the airplane to climb. Conversely, when the control stick is pushed forward, the elevators deflect downwards, reducing the angle of attack and lift, causing the airplane to descend. Lastly, let's discuss rudders. The rudder is a movable control surface located on the vertical stabilizer at the tail of the airplane. The rudder controls the yaw, left or right movement of the aircraft. When the pilot presses the left or right rudder pedal, the rudder deflects accordingly, causing the airplane's nose to point left or right. This movement helps coordinate turns, counteract adverse yaw created by aileron deflection, and maintain stability during flight. In summary, aircraft control surfaces like ailerons, elevators, and rudders are essential components that allow pilots to manipulate the forces of lift, drag, and thrust to steer and stabilize the airplane during flight. Understanding the role and function of these control surfaces is crucial for both pilots and aviation enthusiasts alike.